Oh, hi there. Didn't quite see you. Don't get too close. We have to keep a social distance. I was just doing some discrete math. Would you care to join me? I was just about to do problem 9.6.2. The problem reads, which of these relations on 0, 1, 2, 3 are partial orderings? Determine the properties of a partial ordering that the others lack. So we're only given one problem here. We have the relationship 0, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 2, 2, 3, 3, 0, and 3, 3. The question asks us to determine whether this is a partial ordering, otherwise known as a poset. We know it's a partial ordering if it is reflexive, antisymmetric, and transitive. So let's determine whether it's reflexive first. We know it's reflexive if for every element in our set, reflects back on itself. We see that 0 reflects back on 0, so that's the first element in our set. We have 1 reflecting back on itself, so that's the second element in our set. We have that 2, 2 pairing, so we know that 2 reflects back on itself. And we have the 3, 3 pairing, so 3 also reflects back on itself. Because every element in our set reflects back on itself, we can say that our relationship is reflexive. So now let's determine whether our relationship is anti-reflexive. We know that the only time when xy can exist in the relationship and yx can also exist in the relationship are when x is equal to y. So what that means is that the only symmetric pairings allowed in our relationship are those that are reflexive. So we don't have to check those. Let's instead check the ones where x and y are not equal. So for example, we have the pairing 1, 2. We have to make sure that 2, 1 does not exist in our relationship, and clearly it does not. Next, we have the pairing 1, 3. Does pairing 3, 1 exist in our relationship? The answer is no. Then we have 2, 0. So 2, 0 exists. That means that 0, 2 should not exist if our relationship is antisymmetric. And of course it does not. So that's handled. We have 2, 3, and we do not see 3, 2 anywhere. We have 3, 0, and we do not see 0, 3 anywhere as well. So we can finally, with confidence, say that our relationship is also antisymmetric. Finally, we have to determine whether this relationship is transitive. Well, let's think about it. We have the pairing 1, 2, and we have the pairing 2, 0, right? The right value of this pairing matches the left value of this pairing here. So that means that the pairing 1, 0 must exist somewhere in our relationship if it is transitive. However, we cannot see that. So by counterexample, we say that it is not transitive. Right? We have the pairing 1, 2 in our relationship. We have the pairing 2, 0 in our relationship, but we do not have the pairing 1, 0 in our relationship. So it fails in transitivity in at least one case. So therefore, the entire relationship cannot be transitive. And because it is not transitive, it is not a partial ordering. Let's go on to the next problem. 9.6.4 reads, is S, R a poset if S is a set of all people in the world and A, B exists in the relationship where A and B are people if the first problem reads A weighs more than B. Well, we know it's a poset if it is reflexive, antisymmetric, and transitive. Is it all three of those? Well, the answer is no, right? Let's reword our problem to see if it handles the reflexive case. A weighs more than A. Does this statement make sense? Can A weigh more than A? The answer is no. So it is not reflexive and therefore not a poset. Let's go on to D. A and B do not have a common friend. Is this a poset? Well, we can see that it is reflexive, but it is not antisymmetric, and it is also not transitive, right? Let's consider the case that we have two different people. Maybe one is named Bob and the other's name is Fred. Let's say that Bob and Fred have no friends in common. Then Bob and Fred exist in the relationship, but Fred and Bob also exist in the relationship. So we have a case of symmetry here. So therefore, it is not antisymmetric. We could stop right there and say it's not a poset, but let's keep going. Can we say it is also transitive or not? Well, the answer is no as well. Let's consider the case that we have another group of friends, right? We have Bob, Fred, and maybe Joe as well. Consider Joe, who has no common friends with Fred, while Bob and Joe are both friends with Jim. If this is the case, then we have that Bob and Fred are in the relationship. We have that Fred and Joe are in the relationship. However, we do not have that Bob and Joe are in the relationship. Bob and Joe would have a common friend, so therefore they do not exist in the relationship. And because it fails in transitivity in at least one case, then it is not transitive at all. So we can say for part D as well that it is not a poset because it is neither antisymmetric nor transitive. We have 9.6.6. The question reads, which of these are posets? We have B, so let's begin with that. B has the set of all real numbers. Then we ask whether the set of all real numbers is whether the relationship less than is a poset on the set of all real numbers. So we can already see it's not, right? Because if we have, for example, the value 2, is 2 less than 2? Does the pairing 2, 2 exist in our relationship? And the answer is no. So it is not reflexive. And therefore, not a poset. Let's go on. We have the set of all real numbers, but this time we're given the relationship less than or equal to, right? So we can see that in any case, 2 being less than or equal to 2 holds true. 3, which is less than or equal to 3, holds true. So it is reflexive, but it is also antisymmetric because, for example, if we have some value A which is less than or equal to B, we cannot say that B is less than or equal to A. So it is also antisymmetric. Finally, it is also transitive because if we have some relationship A which is less than or equal to B, and then we have that B is less than or equal to C, then is it not also true that A is less than or equal to C? So therefore, our relationship is reflexive, antisymmetric, and transitive, and therefore is a poset. So we have the next problem, 9.6.8c. It reads, determine whether this 0, 1 matrix represents a poset. So we're given this matrix below. It's important to remember what a adjacency matrix represents, right? And you can also, right, it represents a relationship. So we can create a digraph out of it. So let's do exactly that. We have a 4x4 matrix. So let's create a digraph with 4 nodes. For every 1 in our adjacency matrix, this represents a relationship in our digraph. So let's label the spaces above the rows and columns of our matrix so we can better see how this corresponds to the digraph. We see that 1 and 1 intersect with a 1, so there must exist a relationship between 1 and 1. Again, this holds true for 2, 2, 3, 3, and 4, 4. So all of the nodes reflect on themselves. And then we look at all the other nodes. We have that 1 and 3 have a relationship together. So 1 and 3, so that 1 points to 3. We have that 2 and 3 have a 1 value in the matrix, so 2 points to 3. 4 points to 1, 4 points to 2, and 3 points to 4. So we can represent the same relationship with a digraph as well. So now I'll give you guys a few moments to determine whether this matrix is a poset, right? So go on, try it on your own. I'll just be here. All right, don't mind me. All right, I won't even look. Okay, have you figured it out? First, we ask whether this matrix is reflexive. That is to say that all of the diagonals are a 1, and they are. So our relationship must be reflexive. This is a little more visually apparent in the digraph, that all the nodes reflect on themselves. Next, is it antisymmetric? That is to say, is every value above or below the diagonal, when folded across the diagonal, correspond to a 0? We see that 1 corresponds to a 0. We see that 1 below, again, corresponds to a 0 above. We have a 1 which corresponds to a 0 from top to bottom. And we have a 1 that corresponds to a 0 and here as well. So, because it is antisymmetric in all cases, our relationship is antisymmetric. Is it transitive? Well, we just have to think of one counterexample as to why it might not be transitive. And we can already see it's not transitive, right? We see that there is a 1 in the place of 1, 3. So 1, 3 exists in our relationship. So now we look at all of the values, or all of the 1s on row 3, because this ends with a 3. So we see that this is a 0, so we don't have to check it. This is a 0, so we don't have to check it. This belongs in the same column, so let's skip that. We have a 1 right here, right? 3, we're at this place of 3, 4. So let's write that in as being in our relationship. So if we have both of these values in our relationship, then that means we should have the value 1, 4 if this relationship is really a poset or not, is really a poset. However, we do not have a 1, 4. That is to say, this one and this one intersect at a 0, right? And because of that, we say that 1, 4 is not in the relationship. If it were a transitive, then this 0 would have been a 1, but it's not. So because it fails in transitivity, In at least one case, it is not transitive. Or not a poset. Let's go on. Draw the Hasse diagram for divisibility on the set 2, 3, 5, 10, 11, 15, 25. You might be wondering, what does that mean? You might also see this sometimes in the notation of S, R. So we might have some parentheses on both sides, where this is the set, and we have the relationship on the right side. This is kind of like that S, R notation we've seen before, but they give us that the relationship is divisibility, so that's why they don't have it in that S, R notation. But how do we create a Hasse diagram? Well, we go element by element. So we begin with a 2. It's because we don't have anything yet, no nodes have been drawn, we can just draw the 2 in its place at the start, at the very bottom of our Hasse diagram. Then we go on. We look at 3, and we ask ourselves, does 2 divide 3? And the answer is no. So we create 3 at the bottom, and there is no relationship between 2 and 3. We have 5, and we ask ourselves, does 5 divide, or does 2 divide 5, or does 3 divide 5? And the answer is none of them. So we create a 5 on the same level as 2 and 3, and there is no relationship between them. How about 10? Does 2 divide 10? The answer is yes. So let's create a 10 on the second level of our Hasse diagram and draw a relationship from 2 to 10. In Hasse diagrams, the relationships are not directed, right? So we don't need to write the direction there. 3 does not divide 10, but 5 does divide 10, so we also have a relationship from 10 to 5. We look at 11. Does 11 divide any of the values we have present? The answer is no, so we create 11 by itself on the first level of our Hasse diagram. How about 15? Does 2 divide 15? No. How about 3 and 5? Right? They do. So we have a relationship from 3 to 15 and from 5 to 15. Finally, we have 25. 10 does not divide 25, 15 does not divide 25, 2 does not, 5 does, however. So let's create 25 on the second level of our Hasse diagram and draw a relationship from 5 to 25. We see that although 11 is isolated, it still exists in our Hasse diagram. And then we're done. This would be the correct representation of this set on the relationship of divisibility in like a Hasse diagram form. I wish I left myself more room here, but we'll just go on. So the question reads, answer the questions for the POSET, and they give you a set on the relationship of division. So this is using that same S, R notation that we can also represent our POSET with. So to do any of these problems, we first have to draw our Hasse diagram, right? So we just take all of our elements and plug them in. So there's nothing to begin with, so let's just create a node labeled 2. And then I'm going to let you do the rest by yourself. So go on, try your best. I'll pause the video at this moment and try it yourself, because Hasse diagrams are important, but even more so they are fun. So just try it yourself. I mean, what else do you have to do? We're under quarantine, so does 4 or does 2 divide 4? And the answer is yes. So let's create another node above 2 with a relationship between them. We have a 6. We have a 9. We have a 12. We have an 18. Right? That is to say that 2 can divide 4, but 2 can also divide 12, and 2 can divide 48, 2 can divide 60, 2 can divide 80, 2 can divide 36, 2 can divide 72. The same holds true for 6 and all of the values above it, which are connected to the 6. So we can represent it very easily with a hash diagram, this relationship, right? And we see what does not hold true, right? Because 2 does not divide 9, so there's no relationship. 12 does not divide 9 because you have to go down a level and then up a level to get to 9, right? So because of that, 9 does not divide 12, and this holds true in all cases when it doesn't divide it. Okay, so then we can finally answer our first question. The maximal elements are those which do not have a relationship above them. So anything that acts almost like an endpoint on the top. So that would be 60, because there is no relationship above it. There is no relationship above 48. The same holds true for 72 and 27. Then it asks us to do the same thing, but we find the minimal elements. And of course, that's easy. It's just whatever doesn't have a node below it, or a relationship with a node directly below it. So that's 2 and 9. So 2 and 9 would be our minimal elements. Is there a greatest element? And the answer is yes. There's only one element at the very top, right? It is one level above 60 and 48, and it is 3 levels above 27. So 72 is our greatest element. Do we have a least element? And the answer is no. 2 and 9 are our minimal elements, but we do not have a least element because 2 and 9 are both on the same level. Neither is least than the other. So we do not have a least element. Find the upper bounds of 2, 9. So we look at the elements 2 and we look at the elements 9, and we need to find the upper bounds. Well, those are values which share in the relationship with 2 and 9. We can see that 2 and 9 share 18, right? So 18 would be one of our upper bounds. 6 is not an upper bound because although 6 is divisible by 2, 6 is not divisible by 9 because you cannot go down on the hash diagram and reach the 9. You have to go up and then down. So one of our upper bounds would be 18. But we also see that 36 is another upper bound, and 72 is also another upper bound, right? Because 2 can divide 36, 9 can divide 36, 2 can divide 72, and 9 can also divide 72. Next, find the least upper bound of 2, 9, if it exists. And this is really just the least element of the upper bounds that we have already given. And obviously, that would be 18. 18 is the lowest on the hash diagram of divisibility on the set 9 and 2. Next, find the lower bounds of 60, 72. So this is the same as finding the upper bounds, but going downwards instead. So we have the set 60 and 72, right? What are the lower bounds? Well, we can see that you can go down on both and reach 12. So 12 would be one of our lower bounds. But also 2, 4, and 6 would be other lower bounds, right? 12 is a lower bound, 6 is a lower bound because you can go down from 60 through 12 to get to 6, and you can go down from 36, 18 to get to 6 on the 72. And this, of course, also holds true for the 4 and the 2 as well. So we have 4 lower bounds of 60, 72. Next, find the greatest lower bound of 60, 72 if it exists. So the greatest lower bound would be which of these is the highest, has the highest level in our hash diagram. And the answer would be 12 because it's higher than 2, higher than 4, and higher than 6. So 12 would be our greatest lower bound. We have 9.6.43a. Determine whether this poset represented by this Hasse diagram is a lattice. We know it is a lattice if for every incomparable pair, that is, pairs that don't have a relationship, they have both a greatest lower bound and a least upper bound. So let's first find our incomparable pairings. These would be BC, DE, and DC. You might be wondering, how can I know this, right? We can kind of eyeball it, right? Because, for example, for B comma C, we have to go down and then up to reach C. For B, we have to go, for D, so for D and C, we have to go up and then down our Hasse diagram to reach D from E, as well as C. So because you can't just go up or down like you can for all of the other pairings, right? So we would say that B and G are comparable because you only have to go up to reach G from B. Similarly, you only have to go down to reach B from G, so those are comparable. But for these, you can't do the same thing on our Hasse diagram. So now we have to determine the greatest lower bound, or the GLB, as well as the least upper bound, or the LUB. Does DE have a greatest lower bound? Well, DE does in fact have a greatest lower bound. This is simply the first element that the two meet at below. So we would say B is the greatest lower bound. For D and C, the greatest lower bound is A, right? That is the first element they meet up with from below. Same with BC. Their greatest lower bound is A. Then we look at the least upper bound. For D and E, this would be F, because they first join with F above. For D and C, this is also F, but for B and C, this is E. So we filled out our table. Because we filled it out, all the incomparable pairs have a greatest lower bound as well as a least upper bound. So we say that our poset is indeed a lattice. Find the compatible total order for this poset with this Hasse diagram. Okay, so they've given us the Hasse diagram and they want us to come up with a total ordering. Okay, so to do this, and there are many solutions, right? You know, I'll just give a couple of them, but it's really very easy. You just arbitrarily choose the minimal vertex and then you put it in the set. And you do that until you've used up all of the vertices in your Hasse diagram. And you know, what does arbitrarily mean? Well, arbitrarily just means that you do eeny, meeny, miny, mo on it, and then whatever you land on, that's the one that you choose first. So, you know, let's do that. Eeny, meeny, miny, mo. Okay, so we got A first. So let's put A at the start of our total ordering. You know, now we have a couple of other minimal vertices. D is now a minimal vertex because A has been used up. So now we do eeny, meeny, miny, mo on D, B, and C. So eeny, meeny, miny, mo, B, right? We can choose B for our next one. So we cross off B off of our list. Now we have E, which has opened up as a minimal vertex. So now we can go D, E, or C. Let's go for C, just to get out of the way, right? And we just keep going like this, right? Choosing whichever minimal vertex we want. And you can come up with a total ordering similar to this, right? We can do this another way, for example, by choosing a different vertex to begin with. Instead, let's begin with C, right? So if we begin with C, we cross C off the list, and now we're left with 3 minimal vertices, A, B, and F. Let's go with F next. So we've begun with C, we choose F next, Next, let's take off G, because G has become a minimal vertex. We can arbitrarily choose in our total ordering. Next, not go K, because K is not a minimal vertex in our current Hasse diagram, right? K is not minimal because there's something below K which hasn't been used. So let's go for B. We can go for E or A next. Let's go for E, then let's go for A. So we cross those off the list. After A, we can go with D or H. Let's go with D. We can go with I, H, or H. Let's go with I. So we cross I off that list. Now we have J or H. Or I'm sorry, we do not have J because there is a vertex lower than J. So the only vertex we could take off of our Hasse diagram now is the H. So we take H off of our Hasse diagram. Then we look, we can now choose J or K. Let's take K next. Next, we have L, M, and J. We could either choose J or M, but let's go ahead and choose J. Then we could choose L or M, right? There's only two vertices left, and they're both, there's nothing below them, so we could either choose L or M. Let's go for maybe instead of J, we could choose M, then J, then L. Wonderful. So we've used up all our vertices and we've created another total ordering. So you can do this again, right? Let's do it one more time. We could say that we begin with A, we go to B, right? So there's another total ordering that we could have used as our solution. So we'll do one more. Any one of these would have been a correct, compatible total ordering of our Hasse diagram. And I guess that concludes the recitation